with Prami and Yaroslav from UCLA, and with my supervisor, Rembert. And our work in it concerns local thermomagnonic torques into fluid spin dynamics. So our work is based on a two-fluid view of spin dynamics in magnetic insulators. And this means that we describe the local spin density as the sum of two different components. On one side, you have a zero temperature component, which is given by the ground state value of the local spin density. And this component is proportional to the saturated spin density and the spin density orientational parameter, meaning n, which is a unit vector along the direction of the local spin density. And from now on, I will call this n the order parameter of the system. Now, the order parameter obeys a Landau-Lifshitz-Gilbert-like type of dynamics, and hence its dynamics is collective. And if you want to imagine the simplest example of such a dynamics, you can imagine, for example, a magnetic insulator whose FMR mode is excited via an RF field or microwaves. And this FMR mode is an example of collective spin dynamics. Now, if we switch the temperature on, you will have also fluctuations on top of the ground state value of the local spin density. And the quanta of such fluctuations are thermal magnons. Now, thermal magnons can be visualized as quasi-particles that move diffusively through a magnetic insulating system. And indeed, their dynamics is treated as diffusive dynamics. Now, both the uncoupled dynamics of the order parameter and the thermal magnons are well known and well described. But what escaped much attention up to now is the coupled dynamics between these two components of the local spin density. So here is where our work comes into play and what we focus on. We want to understand the interplay between the diffusive and the collective dynamics, and we want to do it for general spin texture. So namely, we want to describe the torques that thermal magnons exert on the coherent order parameter and the back action of the coherent order parameter on the thermal magnons. We tackled this problem phenomenologically, and then later on we will also substantiate our observation with some microscopic theory that we derived before. But we start phenomenologically by making a few prior assumptions. First, and this has been already discussed quite a lot by Garrett, we assume that the thermalization processes within the thermal cloud are fast enough to equilibrate the thermal magnons to a common temperature and chemical potential. So we can describe the thermal magnons with a well-defined Bose-Einstein distribution. And also we assume that the coherent spin texture is smooth on the scale of the thermal magnon wavelength. So the magnetic variables which describe our system are the thermal cloud density and the order parameter. And then, having defined the magnetic variables, we can also associate to these variables their conjugated forces. The conjugated forces are described as the functional derivative with respect to the corresponding variable of the free energy functional of our system. And for the thermal cloud density, this corresponds to the chemical potential, while for the order parameter, it will be the effective Landau-Lifshitz transverse field. Then, secondly, we look at such system by focusing on linear response, which means that we can describe the rate of change of the magnetic variables as a function of their conjugated force via a linear response matrix. Now we know what are the diagonal elements of such a matrix. So the first diagonal element will account for the uncoupled dynamics of the order parameter. So this is the Landau-Lifshitz-Gilbert type of dynamics, where I'm just neglecting for now Gilbert damping. And secondly, the second of diagonal term instead describes the diffusive dynamics of the thermal magnons. And what we are interested in determining are the form of these two off diagonal terms, which are, I will say it once more, the thermomagnonic torque that the thermal magnon accumulation will exert on the order parameter, and the back action of the dynamical order parameter on the thermal magnons. So we can determine the form of these torques within a very general framework. So since the order parameter is not the magnitude of the order parameter is not a dynamical variable in our system, we can describe we can write down the most general local thermomagnonic torque in the following form, where H is a function which is linear in both the chemical potential and the evolution of the order parameter. And then our derivation is very general and is based on symmetry principle and on Zagier reciprocity. So what you would do effectively would be to start writing all the terms that are allowed by symmetry. So if we consider a system that is invariant under a certain symmetry transformation, also H will have to be invariant under the same symmetry transformation. And secondly, the form of this term has to be constrained by Onsager reciprocity. And here we will impose Onsager reciprocity for both the off-diagonal terms in the linear response matrix, and also the off-diagonal terms in the matrix that describe the transverse order parameter dynamics. So this derivation is general, and you can apply it to a variety of systems, but of course to derive explicitly this torque, you need to make a choice and focus on one type of magnetic system. And in this case, we focused on U1 actually symmetric ferromagnets, so, or in simpler words, easy plane ferromagnets. This is the Hamiltonian of an idealized easy plane ferromagnets. Yeah, also easy axis, yeah. And then this Hamiltonian is invariant for rotation around the z-axis. And also our local thermomagnonic torque will have to respect this invariance. And moreover, U1 symmetry demands also the conservation of the z component of the spin density. And this is an extra requirement that we will impose on the derivation of the local thermomagnonic torques. So here I show you the final form of such torques. Focusing on the evolution of the order parameter, you can see that you will have one term, here the second, that describes how the thermal magnons relax into the coherent order parameter by transferring angular momentum, and then a first term that describes the back action of a dynamical order parameter into the thermal cloud. And the form of this term is very similar to the terms that describe the interaction between spin-polarized electrons and magnetization dynamics at the interface between insulating ferromagnets and metals. So these terms are a spin transfer torque-like term and a spin pumping kind of term. So for now, eta is still a phenomenological parameter that describes the coupling between the coherent and incoherent spin dynamics. But I will try to show you in a second what is the microscopic origin of eta, at least for U1 actually symmetric system. So now I just want to note that this model has been recently used by the group of Amir Yacobi in Harvard. So what they managed to do was to measure the FMR-induced chemical potential of the incoherent magnon gas in YIG. And they used our phenomenological model to extract the strength of the coupling between coherent and incoherent spin dynamics. And it is interesting to note that while this coupling has been ignored up to now, in YIG at least is of the same order of magnitude of Gilbert damping. So it seems that this coupling is instead large enough to the thermal magnons can exert a torque on the order parameter that is large enough to induce magnetization per session. So now I will show you what's the microscopic origin of such a coupling in the systems that we are considering. So first, we have to resort to the form of the Hamiltonian for one actually symmetric system. And the first key ingredient that we need is a finite tilt of the spin density out of plane. So this could be achieved, for example, by applying a magnetic field. And we need this tilt because we need a finite magnon density in our system, obviously, to start with. Also because in this context, I will describe the coupling between coherent and incoherent spin dynamics as the coupling between the ground state magnons and the thermally excited magnons. So obviously we need the magnons to start with, and this can be seen by performing an Austen-Primakov transformation. So mapping the spin density operator into operators that create and annihilate a magnons, and then the finite Z projection of the order parameter can be easily identified with some finite magnon density. And then secondly, after introducing the Austen-Primakov transformation, in analogy with our description of the spin density, we can describe the magnonic field operator also as the sum of two different components. A ground state component, which describe the coherent ground state of the system, plus some fluctuations describing thermal excitations on top of it. And performing the Austen-Primakov transformation, one will finally find out that the interaction term between the ground state magnons and the thermally excited magnons stem from the anisotropy. And these terms are of this kind. So, for example, this term describes two magnons that are scattering into each other, and one of these magnons will lose enough energy to collapse into the ground state. That's also why we dub this process as condensation. And then you can have, of course, you will have the time reversed process, which we'll call evaporation. So to conclude, here the interaction between coherent and incoherent spin dynamics is mediated by the easy plane or the anisotropy in the system. And then you can also put everything together to describe the full dynamics of the system. So if you want to describe both the dynamics of the thermal magnons and the order parameter, you will account for the uncoupled dynamics plus the thermomagnonic torques, describing the interaction between the two. And here we restore only at the end some relaxation mechanism. In general, the underlying assumption of our procedure was that relaxation is weak enough in the system to let us derive the local thermomagnonic torques without accounting for it, and then just being able to restore it at the end. So up to now, I show you a general phenomenology, and I want to give you an example of how such phenomenology could be applied to a system that is of practical interest. And in this case, is a system that sees a coupled superfluid and domain wall motion. So a superfluid has already been discussed in the previous talk. So just to to remind you once more what it is, you can consider a system that has a U1 symmetry. In such a system, the Z component of the spin is a conserved quantity and is also the generator of rotation within the XY plane. And what turns out is that the hydrodynamics of the Z component of the spin density and the azimuthal angle in the XY plane mimics very closely the hydrodynamics of the mass density and phase in classical superfluids. And that's why we call this system spin superfluid. And the resultant spin superflow is determined only by the projected spin texture in the XY plane. So the velocity of the superfluid depends only on the gradient of the azimuthal angle. Now, only last year, Prami, which is one of the co-authors of this paper, and Sequando and Yaroslav came up with this proposal, which envisions a bilayer of an easy plane and easy axis magnets, and one layer will host as a Goldstone mode a spin superfluid, while the easy axis magnet can harbor a domain wall. Now what they imagined was to put here an incoherent spin source, such as a metallic lid, and via a spin accumulation exert a spin transfer torque on the coherent order parameter in the easy plane. So such a spin transfer torque would trigger the motion of the spin superfluid in the easy plane magnet. And since the easy plane magnet and the easy axis magnet are assumed to be coupled, then the superfluid motion would be blocked due to the coupling with the domain wall region, and the angular momentum would be transferred to the domain wall region and trigger the motion of a domain wall. So there have been already quite a few proposals that envision instead a domain wall motion triggered by thermal magnons. And this proposal definitely takes a step forward, because it removes the ohmic dissipation that is associated with thermal magnons. And moreover, this spin superfluid can decay linearly with the length of the channel in which it's propagating, differently from thermal magnons that decay exponentially. So this type of proposal already presents quite a few more advantages with respect to just triggering the domain wall motion via thermal magnons. But then our question was, can we move even a step forward and just remove directly all the conducting components in the system? So remove altogether the ohmic losses. And theoretically, the answer is yes. We can remove the electronic medium and substitute it with the heat conductor and still have a system with the same functionality. So the idea is that if you put the heat conductor here at the interface with the bilayer, this will give rise to a thermal gradient. Now, we all well know that a thermal gradient in a magnetic insulator via the spin-Seebeck effect gives rise to a pile-up of thermal magnons. So if we have a pile-up of thermal magnons at the interface, so we have an imbalance of thermal magnons and a finite chemical potential describing this imbalance. They will try to relax. And if you assume and if you accept the existence of this interaction between coherent spin dynamics and thermal magnons, you know that they can relax by transferring angular momentum to the coherent order parameter. And by doing so, they will exert a torque which is pretty much analogous to the spin transfer torque that the electronic medium would have exerted on the coherent order parameter, and they can trigger the spin superfluid dynamics. So the two key ingredients of such a system are, first, the spontaneous breaking of a U1 Z2 symmetry. A U1 symmetry, the spontaneous breaking of the U1 symmetry results into a Goldstone mode, which is a spin superfluid, while the spontaneous breaking of the time reversal symmetry results into a domain wall. And in general, this is applicable to any system that can host such a spontaneous symmetry breaking. Secondly, what we need is an exchange coupling within the layers. First, this exchange coupling acts on the easy plane ferromagnet as an effective magnetic field. So it gives rise to a finite Z projection of the order parameter. And by doing so, it enables for the interaction between coherent and incoherent spin dynamics. And secondly, we need such an exchange because this exchange will ultimately lock the azimuthal angle of the easy plane and easy axis order parameter in the domain wall region. So what happens is the following, that the superfluid will start propagating, and as I told you, the velocity of the superfluid is just determined by the gradient of the azimuthal angle. If at a certain point the azimuthal angle is locked, the superfluid velocity will decrease. And there will be a loss of angular momentum by the superfluid component. Anyway, all the system displays a U1 symmetry. So the Z component of angular momentum needs to be conserved and needs to go somewhere, and it will ultimately be transferred to the easy axis magnet, and it will be converted in a domain wall motion. So we just briefly, we look at this system and we describe the easy plane order parameter and the magnon density in the easy plane ferromagnet, as I've been showing you before in the context of thermomagnonic torques. So we account for both LLG dynamics and diffusive dynamics and the interaction between the two components. And then the easy axis order parameter can be described by the collective coordinates approach. So namely, the dynamics of the magnet reduces to the dynamics of the domain wall. So here, I will be a bit repetitive, but that's indeed what happens. You can see that you induce a thermal gradient, and this will give rise to an imbalance in the chemical potential of thermal magnons. And now thermal magnons can relax into the order parameter. So I'm plotting here the superfluid current. And the superfluid current within this region goes from a vanishing value to a finite value, and then it propagates through the system and decays linearly as expected until it encounters a domain wall region. Here, the transfer of angular momentum that I've described occurs, and the superfluid current decreases abruptly, and this gives rise to the domain wall motion. We also calculated explicitly the velocity, so you can find an analytical expression for it, and it turns out very reasonably that it's proportional to the magnitude of the interaction between thermal magnons and the coherent order parameter, and the denominator instead is augmented by Gilbert damping spin leakage, both in the easy plane magnet and in the easy axis magnet. And with this, I came to my conclusion. So what I tried to explain you is that we derive a general phenomenology that describes the interaction between coherent and incoherent spin dynamics in ferromagnetic insulator. And then I worked out explicitly this phenomenology for U1 actually symmetric system. And as an example of the utility of knowing such interaction, I show you that a local heat flux can induce a distant motion of a domain wall by a spin superfluid. And in general, I think that this open more general and new perspective for the conversion of heat into long-range spin transfer that suffers little dissipation. With this, thanks a lot for your attention.
We have time for some questions.
Hi.
Hi.
I try to understand this superfluid transport.
Yeah.
So I understand that you have some kind of phase gradient in your easy plane ferromagnet.
Yeah.
Is that now also a